So welcome everybody back to our Gamma seminar. Today we have the pleasure to guest Julia Lange from the Department of Mathematical Methods and Physics and at the University of Warsaw. Is going to talk about the reduction and projection of treaties Poisson manifolds via Dirac structures. So Julia, the floor is yours. Thank you for accepting our invitation.
Yes, thank you for giving me a chance to talk about the reduction and projection of twisted Poisson manifolds via Dirac structure. So this talk is the continuation of the talk I've given in the first semester on Courant algebroids and Dirac structures, where I have discussed the technicalities which lie behind Dirac structures. So let me remind you quickly the scheme we went through. We started with defining a Lie algebroid. So it was some vector bundle E to M. We had a Lie bracket and some anchor map, which is not important here. So this is a Lie algebroid. Then we can generalize this structure into Courant algebroids, which was also the vector bundle together with some brackets, which is no longer a Lie bracket in this case. So I will denote it in different notation. We had some symmetric bilinear form and also this anchor map. So there were a few technical conditions that had to be satisfied in these Courant algebroids, which were presented on my last seminar, but will not be needed this time really, because I want to focus on Dirac structure apart from this Courant algebroid structure. So then we can construct, we can consider some subbundle of E, and in order for D to be Dirac structure, D has to be maximally isotropic, and the sections of D has to be closed under the Courant bracket. However, what is important that whenever Courant bracket is exact, which means that the sequence of this form is exact, then it means that the bilinear form has a split signature. So it means that, so this is an exact sequence. Then it turns out that this bilinear form has split signature, which then implies that the rank of D equals dimension of M. And it also means that the E is isomorphic to the generalized tangent bundle of M, which is just Pointragin sum of tangent bundle and cotangent bundle. So, so practically in most cases, we just assume E to be this generalized tangent bundle. And many authors deal with and introduce Dirac structures apart from the whole technicality regarding Courant algebroids, simply just a specific subbundle of this generalized tangent bundle with some given bracket and bilinear form. And this is how I would like to start right now with defining Dirac structures. Okay, so here it is. We just consider this generalized tangent bundle with natural projections onto the tangent space and cotangent space, and we define a symmetric bilinear 2 form, which is defined just by as the contractions of corresponding vector fields with one forms. And we define the Dorfman bracket by this formula. So this is the standard bracket of vector fields, and we also have lead derivative and contraction with differential of the other form. Last time I mentioned that there are different ways to define this bracket. Normally we would say that this is just some Courant bracket which has to have some properties. As you can see, this bracket is not antisymmetric. Other authors sometimes define this bracket to be antisymmetric. However, like for example, we can define this bracket like this. Oh, sorry, there should be y. So we can see that this bracket is indeed antisymmetric, but it does not satisfy Jacobi identity. And where we are more interested, we would like this bracket to satisfy Jacobi identity, which is this case, the Dorfman bracket, okay? But it doesn't make actually much difference, because when we consider Dirac structures, on the sections of Dirac structures, these brackets would agree. And indeed, you can observe that whenever we take the sections of a Dirac structure, then because D is Lagrangian, oh, I forgot to mention that this condition of D being maximally isotropic, when we consider E to be Tm, then it means that D is Lagrangian. So further on, we will only consider the cases where orthogonal of D is equal to D, okay? So whenever we take the sections of D, then this bracket, Dorfman bracket, becomes indeed antisymmetric, okay? So once again, I will remind you this definition. So Dirac structure on this is the subbundle of the generalized tangent bundle of M. Is such that D is Lagrangian and the sections of D are closed under the Dorfman bracket. And we can also recall from the previous talk I gave that there is a relation between Dirac structures and Poisson and presymplectic ones. Namely, if we consider a bivector field lambda and the bundle and the subbundle in Tm formed by the elements that belong to the graph of minus lambda, then this bundle is indeed a Dirac structure. But if and only if lambda is a Poisson bivector, this means that the Schouten bracket of lambda is equal to 0. Similarly, if we have some differential two form, then the subbundle, which consists of the elements that belong to the graph of omega, is also a Dirac structure if and only if omega is a presymplectic form, which means that the exterior derivative of omega is equal to 0. It's easy to see that those subbundles are automatically Lagrangian. However, the conditions regarding bivector field lambda and differential to form omega guarantee that the sections of those subbundles are closed under the bracket. Okay. And now we would like to generalize these considerations by introducing a specific case of an almost Poisson structure, which is twisted Poisson one, which consists of a manifold by vector field on E and some closed free form phi. So this is a closed free form. And the relation between lambda and phi is the following. So we have that the Schouten bracket of lambda is no longer 0. So it's not a Poisson bivector. Okay. What is important is that in order to have this structure, M needs to be at least of dimension 4. If it's not the case, the bracket will always equal to 0, and the twisted Poisson is simply a Poisson structure. Okay, if you're not familiar with what a Schouten bracket is, so here is how we define it on multi-vector fields. So yeah, you can see this formula here, which describes how we would calculate the Schouten bracket of multi-vector fields. So we can observe if we have the Schouten bracket of lambdas, which are bivector fields, in turn, we obtain some three-vector field. Okay, there's some simple example how we do that. So we can consider M of 4 dimensions with coordinates x1, x2, x3, x4. And we define a bivector field by this formula. And simple calculation shows that the terms that would not vanish in this Schouten bracket would be exactly this. There are two terms which will not vanish, and they will be the same. Okay, so this will be so using the formula for the Schouten bracket, we obtain something like that. And the second term will be exactly the same. So I will write 2 in front of it. And we get 2 times x1 yeah, so changing the indices would give us this result. And then one might calculate the 3-form phi, which would satisfy this condition here. One way to do that is just to contract these things with some general one forms. So we would need to solve the following equation. Okay, it's not very difficult to do that. So in our case, we would get this form of phi that would satisfy the condition for twisted Poisson manifold, okay? Yeah. So just like we had the correspondence of Poisson manifolds with presymplectic manifolds, the twisted Poisson ones correspond to almost symplectic ones. So now the question is how to obtain Dirac structures as the graphs of minus lambda and omega, where they came from those more general structures. The answer is pretty straightforward. We just need to change the Dorfman bracket a little bit. So now we use the same structure made on generalized tangent bundle with the same projections onto tangent and cotangent spaces. the symmetric bilinearity form remains unchanged. However, we define the twisted Dorfman bracket just by adding one term, which is related to this closed three form phi. So you can see it's basically the same, but there's just one additional term. Okay. Yeah, and now we define a phi Dirac structures just similar to the previous case. Once again, D has to be Lagrangian, and the sections of D are closed under this new twisted Dorfman bracket. Okay. And just as previously, the subbundles, which consist of the elements that belong to the graph of minus lambda, are indeed phi Dirac structures, if and only if there is a relation between the bivector field lambda and phi, such that M lambda phi is a twisted Poisson manifold. So this condition must be satisfied. Okay, and then the sections of this D minus lambda are closed under the twisted Dorfman bracket. And similarly, if we consider some differential to form on M, then also the subbundle, which consists of the elements that belong to the graph of omega, will also be closed under the twisted bracket. But the condition here will be that the exterior derivative of omega equals minus phi. And once again, these conditions are just to ensure that the sections are closed under the twisted bracket. But, yeah, because naturally, once again, these subbundles by construction are Lagrangian. Okay, I can also mention that it might be confusing sometimes. If we say that something is Dirac subbundle, we only mean that those are Lagrangian subbundles. When we say something is Dirac structure, then we also mean that it is the sections are closed under the bracket. Okay. Now I would like to proceed to the procedure which is called stretching of Dirac structures, which is very important when we want to either project or reduce Dirac structures. So if we are given some Dirac structure and some other subbundle S, which is isotropic, then we define a subbundle ds by the following formula. It's easy to see that by construction, this subbundle is actually Lagrangian. This is the calculation which shows that. However, in general, the sections of ds are not closed under the Dorfman bracket, phi Dorfman bracket, or the Courant bracket in general. Okay, so we have a useful lemma which describes which sections of ds are closed under the bracket. Yeah, so if we assume that D is a Dirac structure, then of course the sections of D are closed with respect to the Courant bracket in our generalized tangent bundle. And we have to assume that the sections on S of S are also closed. We also assumed S to be isotropic as before.
Julia?
Yep.
Okay, I see that you hear me. Maybe I had a problem with the microphone. Maybe there is a typo, yeah? However, S including sign S orthogonal, yeah, before the reduction.
Oh, there. Yeah. You mean that?
Yeah,
yeah.
That.
Yeah.
It's another thing. It was before about talking about data structures. twisted Dirac structures, they can be considered as a certain type of foliations, yeah, because in the case of the Dirac structure, you had that this amounts to the fact that the manifold is foliated by presymplectic manifold, yeah, glued together in some manner, and with the twisted Dirac, it could be what? It could be one of these structures, yeah? Every one of the leaves must be what?
You mean the integrals of manifolds?
Yeah, I mean.
Oh, okay.
What do you think?
I don't know if I understand the question.
The question is that when you have a Dirac structure, a normal one, yeah, you can consider a Dirac structure amounts to a foliation of the manifold as presymplectic submanifold.
Yeah.
And in this case, how this foliation could lie? Because I don't know if there is a similar theorem for twisted Poisson or twisted Dirac structures about how they look locally, yeah? So what I was asking is whether you can consider twisted Poisson or general twisted Dirac manifolds as a certain type of foliation. Have you thought of it? Do you have an idea?
No, I haven't. Maybe you know something about it. Probably you do.
I know a little bit about it, but I'm not sure now about it. When you were talking, I was thinking of it. I made some questions, but you didn't hear me because I had a problem with the microphone. Okay. And anyhow, it's something that's it's a curiosity. Okay, I don't know if it can be interesting, but it's just.
But I assume everything works here analogously because we just changed the brackets and.
Yeah, you know now I remember that there was a paper by how is this girl from Argentina come on, Naranjo, I think is Balseiro, Paula Balseiro and Naranjo. And I think that one of the results was that when you have a certain integrable foliation, and for then it should be regular, you can always consider it as related to a twisted Poisson structure, something of the sort. And I don't remember exactly. And they said something that they don't know whether some similar can be done in the case of irregular and not regular distribution. So maybe something of this sort, but I'm not sure. Yeah, that's.
I remember some condition assuming that the characteristic distribution of lambda intersection with H is regular.
Oh, this is for the integrable, yeah? Integrability?
I'm not sure about the details, but this is just something I remember reading. I don't know what it said further, actually, but there was some consideration of this case.
Okay, you can continue, please. Thank you. I didn't
okay.
think of it. Thank you.
Yeah, so let's continue with these stretched Dirac structures. So yeah, there is a lemma which tells us which sections of the S are closed under the Courant bracket, right? Of course, the Courant bracket will be Dorfman bracket or phi Dorfman bracket, depending on the case. So we need to assume that the sections of S are closed under the bracket, and then the condition would be that this set will consist of those sections of the S which are invariant relative to the Courant bracket. This space we call S invariant sections of the S. Okay, so remember that for later part. Okay, and now let's proceed to reduction of twisted Poisson manifolds. So we are particularly interested in two types of stretching of Dirac structures when S will be considered as some sub-bundle of tangent bundle or of cotangent bundle. This is the case where we assume S to be a sub-bundle of cotangent bundle, yeah? Because we assume we have some sub-bundle H in Tm, which is an involutive distribution. And then we define nu as the annihilator, so it will be a part of cotangent bundle, yeah? So here S will be identified with nu, which lies in cotangent bundle. Okay, so we do this type of stretching, and then if we do, then it follows immediately that this stretched Dirac structure, this stretched subbundle is a Dirac structure. Okay, like I said before, we already know that this subbundle is Lagrangian, so we would need to prove only that the sections are closed. One could observe that the elements of this stretched subbundle will be just something like this. Yeah, where x plus psi is the element of our Dirac structure with the condition that x belongs to H and nu belongs to the annihilator. Okay, so this is a useful form to just ensure that the bracket is closed. Okay. So with these stretched Dirac structures, I haven't said anything about their relation to twisted Poisson or Poisson manifolds. So we are particularly interested in the case where our Dirac structures are related to those twisted or Poisson structures. So how to make sure that our Dirac structure is indeed the graph of some bivector field? We once again consider those stretching along the nu, which is the annihilator of H, where H is just some bundle in Tm. Yeah, so the question is whether the stretched Dirac structure, the stretched subbundle, which is a Dirac structure, is related to some bivector field lambda prime, okay, which is a twisted Poisson bivector. To ensure that, we only need to see that the projection of the stretched subbundle is equal the whole cotangent space. And then this condition may be rewritten in the form that the stretched subbundle plus Tm equals the whole generalized tangent space. And then we can take the orthogonal. So it's equivalent to saying that the orthogonal to this subbundle equals 0. And the left-hand side, one can prove that is exactly this. Okay, so these two conditions are equivalent. Further on, we can also consider that we can consider the case where D is already inherited from some twisted Poisson structure, okay? So it's something like that. Yeah, and then stretching of this Dirac structure, which is related to some twisted Poisson manifold. Yeah, there's also the question where when this is the case. So yeah, we further assume that the initial Dirac structure is also related to some twisted Poisson structure, and rewriting both of these conditions above here leads to this one. Okay, so this is a very useful condition to say that that the stretched Dirac structure of some Dirac structure which is related to twisted Poisson structure is also related to some other twisted Poisson structure. Okay, I know it might be complicated a little bit. Okay, we can also consider a very specific case where H is just the characteristic distribution of lambda, which is this, and then nu becomes the kernel of lambda, and in turn one can see that stretching does not change the Dirac structure. Okay, so we end up with the same Dirac structure. Okay, and now we can proceed to reduction of twisted Poisson manifolds. So there is a proposition which says that whenever we have a Dirac structure of this generalized tangent bundle, and we have some integral submanifold n of m, so we have some submersion n to m, this proposition says that under certain conditions, we can obtain a twisted Poisson, like a Dirac structure which comes from twisted Poisson structure on the generalized tangent bundle of n. Okay. Yeah, so we need to have a integrable distribution on M, which is of rank K, and some Dirac structure, which is associated with some twisted Poisson manifolds. So we can write that D equals D minus lambda for this lambda here. And N would be the integrable submanifold, integral submanifold of H. And then we restrict the stretched Dirac structures along the annihilator of H to the points of N. So whenever it's a vector bundle of N, it is endowed with the natural differential structure of which exists on the generalized tangent bundle on M. And we can from the elements here, we can construct elements which belong to the generalized tangent bundle of N. So this is once again the graph of minus lambda. Yeah, and the proposition says that we are given a new Dirac structure with respect to some inherited, with some structure on this cotangent bundle of this generalized tangent bundle on N with new free form phi related to our initial phi. Yeah, even only if the restrictions of covectors here to H restricted to N has rank K. Okay, so this is the reduction of Dirac structures which come from twisted Poisson structures. Now, I would like to consider projections along an integrable distribution. So now we once again, we would consider stretched Dirac structure, but in this case, S would be just a subbundle of tangent bundle, not a cotangent one. Okay, so we will consider now the stretching of this form, where H is just a bundle in Tm, which is integrable. Okay, and now we can consider projections of M to the space M over H. We assume it is a submersion, and these are subbundles. And we need to define the objects which are projectable, which exist on M, and which are projectable through the projections onto the quotient space, right? So here are the definitions for the projectable functions on M. Here, projectable vector fields, bivector fields, any K forms. Yeah, this is pretty technical, but I don't think we should get into details here. So there is a proposition that the space of projectable sections in the stretched bundle, the stretched Dirac structure with H being subbundle of Tm, which is integrable. And the proposition says that the space of projectable sections are closed under the Courant bracket. So it means it is, one can see that this is exactly the space of H invariant sections in D. It was defined here, okay? So one can see that this projectable sections is equal to gamma H DH. Okay, and another definition we say is that H leaves D invariant if for every point in M and the element like this, there exists a projectable section E which takes values in the stretched Dirac structures through the subbundle H. Yeah, so we have a correspondence that this section at every point P in M equals just XP plus Xi P. Yeah. And there is a further observation that if H leaves D invariant, then the stretched Dirac structure DH is projectable onto the quotient space M over H. So whenever we have some elements that belong to the stretched bundle, there is we can transfer them onto the generalized tangent space to the quotient space. Okay. Yeah. And on this bundle, we would have a new Dirac phi Dirac structure, which is of course related to the first one on the M. Okay, there is also another proposition that if lambda is projectable relative to our projection onto a quotient space, then the H leaves the Dirac structure D minus lambda invariant. Yeah, and there's also some other observation which we've made, that whenever you have a whenever you start with some D being a phi Dirac structure on this bundle. And it gives a projection through the H onto the quotient space. So we have some new Dirac structure on the quotient space, which is related to the twisted Poisson structure. So we have some lambda prime related by definition with some closed free form 5 prime. The question would be whether there exists on Tm some Dirac structure which gives the same projection but is related to twisted Poisson structure. And the answer is yes. We can always find some Dirac structure above which is related to twisted Poisson manifold which gives the same projection. Okay, and now we could consider combining projection and reducing twisted Poisson manifolds via Dirac structures. The scheme would go like this. So let's say we have some Dirac structure on the on generalized tangent bundle on M. Then through stretching, we would obtain some structure on the quotient space. Or we can also go the other way around by stretching through the D nu onto some integral submanifold of M. And then we can project this onto the space just like this. And the question would be, it seems to work. However, we still need to check some things. So the aim would be to obtain the same structure at the end, going two different ways, using stretching and projection. Okay, reducing and projection. Yes, so maybe if I'm done with that, I could give a talk maybe next semester describing these things. So here's the bibliography. I specifically recommend this one if you want to read about some applications of these types of structures. Yeah, and very nice source on the knowledge of Dirac structures at all would be this one. Okay, and basically the things I've talked about today are the generalization of the things which are said here. Okay, thank you for your attention.
Is there a question, remark? So I do have a question. Julia, can you recall how this reduction can be used to obtain all the results in the literature?
You mean the reduction
Yeah, how you can recall for the geometric structures?
Because this is the scheme for the so-called Marsden ratio reduction, right? Ratio reduction.
Yeah. But you know, you are doing but a very quite general structure, but twisted and Dirac structures. As particular cases, could you comment on all the particular geometric structures to which you can apply this thing and you can retrieve as a particular case? Because you know there are people doing Marsden-Bison reduction about with respect to all the structures in literature. Yeah, so it could be interesting how this retrieves all these all the stuff made by others in just a unifying framework. For example, does it work for almost symplectic, conformally locally symplectic structures?
It should, because we would have the relation of the bivector with this two form, right?
Yeah, it works, yeah. And
yeah, because we can always transfer it from lambda to omega, right?
yeah, that's nice.
So yeah. We particularly focused on these twisted Poisson structures, but it's no problem to change the way of describing things using just the two form omega.
Yeah, and for example, for Jacobi, it could work.
Yes.
Yeah.
We can also obtain a Hamilton-Jacobi theory for this type of twisted Poisson structures.
This is a nice thing, because there are several works dealing with it. With particular cases, we could retrieve them all in a unifying scheme, and particular examples that they are even canonical in this stuff could be used to find reductions in previous works. I mean, there are, for example, I think that it was locally simplex, locally conformal. No, it was for.
Yeah, so I think it would be interesting when we are done with this reduction to also include the Hamilton-Jacobi theory, because then it's very hard to find the examples which are physical, of course.
Yeah.
In this.
Anyhow, is for these many of these words, there's the usual stuff. I mean, that they're even in certain types of geometries that they can be described by means twisted and Dirac structures, or twisted Poisson structures. The problem is that they are not able even to find Hamiltonian system. Yeah, this type is so complicated. These structures are not very well known, that sometimes they don't know how to apply it even academical examples. Yeah. Okay. So thank you.
Yeah. Thanks. Thank you for your attention.
And see you in a week, everyone. Bye.
Bye. See you.
I think there is